And so now we shall move to our final speaker of the day, James Drew from Stanford. He's a professor of biomedical data science and also has courtesy appointments in computer science and electrical engineering. He's also an inaugural Chan Zuckerberg investigator at the faculty there, and involved in their AI for Health program. So James, all to you.
Great, thank you very much, George. And thanks also for organizing this really exciting workshop. Really enjoyed the previous presentations. Yeah, so excited to meet all of you. And I'd like to share some of the work that we've been doing, taking sort of a data-centric perspective on interpretability and AI. Now, as George mentioned, a lot of our efforts in my group are interested in developing machine learning tools for biomedical applications, right? So in biomedical applications, that's where especially a lot of these techniques for interpretability and trustworthiness becomes very relevant and very salient. So what I want to do first is to actually give you two examples based on some of the recent work that we've done of where quite sophisticated machine learning algorithms actually broke, right? And I want to give you these two examples where they broke just to motivate the rest of the presentation. So one example will come from the medical setting, the one from non-medical setting. So the first example I want to mention is looking at large language models, right? So this is in particular looking at GPT-3, which is one of these very large language models from OpenAI, which has garnered a ton of attention from our communities. And how they work is that you can enter a prompt in text, and the model would automatically generate text based on that prompt. So I'm going to play for you a video of my student, Abu Bakr, interacting with GPT-3, sort of a live interaction. So Abu would enter 2 Muslims, and then the rest of the text is automatically generated by this AI model. And what you can see is that the model starts to generate texts that have a very strong association of violence to Muslims, right? Here it says they slaughtered 85 people. And when we change the prompt, right, you can put in different prompts, the model will give different text, right, but it will still generate violent content for Muslims. Here it says something about terrorists. And finally, Abu got fed up and wrote explicitly that the Muslims walked in to worship peacefully, but the AI model was not deterred and wrote that they were shot dead for their faith. So this is, a model is quite state of the art, right? But in this case, it clearly exhibits, these strong and problematic stereotypes and we quantified this quite systematically, right? So basically, if you do these experiments and we design probes to sort of look for these, to quantify the stereotypes in this GPT-3 model, and what we found is that in 70% of the instances, the model would generate content that would associate Muslims with some notion of violence. Right? And we similarly characterize it has also stereotypes for other ethnic, religious, and gender groups as well. Right? So this is clearly quite a vivid example of a state-of-the-art machine learning model that has unexpected consequences and broke in this particular way. So the second example where the AI broke is comes from a medical application. Now, if you think about applications of AI in healthcare settings, these dermatology applications are some of the most at the forefront of AI in healthcare. And the reason for this is that the data for dermatology is relatively easy to collect, right? Oftentimes you can just take your phone and take an image of your skin, and there are algorithms, including, for example, ones developed by Google and other companies that could analyze those images and tell you what is the diagnosis. Right. So they're starting to become more and more of these algorithms that are becoming commercially available to do diagnosis based on patient images. Right. In this particular case, if you send in this image, right, the algorithm would say that, oh, this is likely to be melanoma, which would be a very serious outcome, right? It's a type of cancer, and you should go see a dermatologist as soon as possible. Now, if you look at the published performance of these models, these are all quite respectable, very good performances. Right, something about 0.9 or 0.95 AUC. And what we decided to do was to see, okay, so how well would these models work, on a new data set, right? So I had a terrific postdoc, Roxana. Roxana has a weapon in that she's actually a practicing dermatologist in addition to being an AI researcher. So we collected a new data set here at Stanford that we're calling the Stanford Diverse Skin Data Set. Right? And we just simply run these algorithms, several of them, just off the shelf on our new data set. And the performance of these algorithms just completely cratered, right? In this case, it dropped from 0.93 to 0.6. So that was actually quite surprising to us because these were quite popular state-of-the-art models. And the big mystery is, why did the model break, right? So what caused the AI system to perform to drop so much on an entirely natural, non-adversarial data set? Okay, so to understand in both cases, what led to these mistakes and how to understand how to prevent them from happening in the future, what we really want is to need to understand is what is the data that went into training and to testing each of these different algorithms, right? And this is, I think, a part of quite a general phenomenon, quite a general shift in our machine learning communities, whereby if we really want to explain the behavior of AI systems, right, we really need to understand what is the data behind these algorithms and what are the interactions between different types of data, right? And this is especially the case as we're trying to take AI models from the research sandbox into real world deployment. So this is why I've been really fascinated and want to share with you this data-centric perspective that we have about explainable, interpretable AI, right? So I'll come back to at the end of the talk to explain to you exactly what happens in the dermatology AI algorithm, right? And to explain what was the reason why the performance dropped so much. But before I do that, I want to sort of take you through the process, right, through which we actually arrived at these answers. And this is a general framework of this data-centric interpretable AI framework that I think can be applied to other medical applications, also to other AI applications, in finance, in consumers, in other domains of science. So when I think about this problem, there are basically sort of three questions that I would like to ask, right? And that forms sort of the three steps of this framework. So the first question that we want to understand is, what is the data that went into training and also critically to testing these models? Right. Then the second step is, how can we, once we know what data went into training it, can we actually quantify how different types of data and how different sources of data all interact and contribute to the model's success or to the model's mistakes, right? I would like to do that mathematically and more quantitatively. And the third component is that we would like to have a way to collect much more human-in-the-loop data to perform real-time monitorings and auditings of these AI systems, right? This is also a topic that came up through several of the previous talks, including the previous one by David, and also some of the earlier ones by Anima, for example. Okay, so I'll just briefly go through each of these steps in the next about 15, 20 minutes, and then come back and tell you, okay, so through these steps, how can we explain what actually happened in the dermatology AI mystery? Okay, so the first part, the starting points that we just need to have much better ways to characterize the different types of data that goes behind these AI algorithms. So as an example, so I'll use the dermatology sort of as a running example, but I think that these ideas can be applied quite broadly. Right, so for the dermatology setting, one thing we did was to basically create a survey of the landscape of all of the data sets that went into training different dermatology AI algorithms. So this is summarized in this graphic visualization here. So each of the squares here corresponds to one of the published dermatology AI algorithms, right? It's a published paper. So the number just corresponds to the index of the paper. So the circles here are the different data sets. Right, so there are two types of circles. The red circles are where the data sets are private, right? So that means that nobody else can access to that data set. And the green ones are the public data sets where through some process you can actually gain access to that data set. The size of the circle corresponds to the number of samples in that data set. Right, so there's a lot of interesting things. I just want to highlight a couple of them. Right, so first is that you can notice that there's a few public benchmark data sets, right, like this large one here, where a large number of algorithms are all built and evaluated on this data set. Right. On the other hand, there's about half of the algorithms, right, these ones on the top here, they're all basically trained and evaluated mostly on relatively small and private data sets. Right. And this actually means that it's actually extremely difficult for us to really know what's going on behind these algorithms. Right? It's very hard for us to audit these algorithms because we don't have access to the data and we don't know what is really the composition of the data sets. So I think it's really important to do these kinds of data to algorithm maps, right, and surveys across different domains. Right? So we did this also for other medical settings, right? So here it's a similar kinds of survey that we did. It was published earlier this year, looking at all of the FDA-approved medical AI devices. Right? So typically, you think about the FDA as sort of the gold standard of evaluation, right? FDA has to approve the vaccine before they're being used on us, or they have to approve the cancer treatments, right? So in the last few years, there's also increasing number of AI systems and devices that also have been approved by the FDA. And we're interested in seeing, okay, so what was actually the data that went into testing and evaluating these systems before they got FDA approval? So each of the symbols here corresponds to one of the FDA-approved AI algorithms, which is, I just stratified them by which body part that they apply to. So maybe the most important thing to note here is the color, right? So the algorithm, the device is shaded gray if that device did not report evaluation from multiple locations, right? So more specifically, about 90 of the 130 algorithms did not report multi-site evaluation, right? And as machine learning researchers, right, so this should really raise a red flag because we know well that the model's performance can be highly variable across different sites, right? And as we saw from the dermatology case, right, so the performance can vary by 30, 40% across different locations, right? So the lack of multi-site evaluation, we think, can really mask important vulnerabilities in the performance and potential weaknesses of these models. So these are just a couple of examples, and I really think that doing more of these kind of data surveys is an important first step towards building more, having better explanations and trust for our behaviors of our AI algorithms. So now that we know what data goes into a particular algorithm, the second step is that we want to take a much deeper look to understand, in a given data set, right? So how do the different parts of the data contribute and interact to impact the model's behavior? So what does that mean more concretely, right? So I want to sort of just briefly introduce this notion that we're calling the data accountability in machine learning. Right, so most of the machine learning frameworks have sort of the following flavor, right? So you have some data sets, right? In this case, I show 3 example data points, right? And you put them into your favorite learning algorithm, and you measure their performance by your favorite metric, right? So in this particular example, let's say if your algorithm achieves 80% performance, 80% accuracy, right? What I'd like to do ideally is to understand, how much did each of my individual training data points, right, contribute to the model's 80% accuracy, right? So mathematically, that corresponds to, ideally, I want to partition that 0.8 to each of my 3 training points, right? So each of the symbols here, you can think of them, as, for example, data from a particular patient or data from a specific source of patients, or it could be from one hospital. And that's also important for understanding the mistakes of the models, right? So for example, if the model exhibits some biases, as we saw before, or if it has mistakes, I would like to understand, what source of my data contributed to that bias or to that mistake, right? So if I really want to understand and have transparencies about how this whole pipeline works, I think this data accountability is an important ingredient. Okay, so a lot of the technical work we've been doing is to try to make this into a actual practical framework, right? So it comes down to thinking about how do we quantify the value and impact of different data points. Right, so I want to give you sort of just the intuition of how this works, and then there's a lot more details that are in the technical papers, which I'll point to at the end. So here's the intuition, right? So if I have these 3 data points, and if I want to understand what is the impact of this point, they say the start point here in the middle, right? So the most simple thing I can do is I can train 2 models, right? The first model is on all of my data points. Second model is on the remaining data points after I remove this point star, right? And I can see how does the decision boundary of the model changes and I quantify the change in model's performance. So it's actually commonly used in statistics to sort of as leave one out scores, also by other names like leverage scores. And it's also in machine learning called like these kind of influence scores, which are basically approximations of leave one out. And it turned out for several reasons that leave one out scores are not very reliable, right? They can be very noisy. So this has motivated us to develop this idea of called data Shapley scores. So it's very closely related to leave one out, right? So what you do here is that instead of doing this, leave out this data point star once, we're going to create several different scenarios and see in each scenario, what is the impact of adding or removing this point of interest, the star point, right? So in this illustration, I'm showing you here sort of 3 different scenarios. Each scenario now corresponds to a different random subset of my training data, right? And I'm going to take that different random subset and I'll say, okay, so what happens if I add or remove this point star, right? So I can compute the change in my performance in each of the scenarios that sort of quantifies the impact of this point star in that scenario, right? And there's a unique way to aggregate these scores together into one score for each of the data points. That's what we call the data Shapley score, right? So there's a mathematical way to do exactly what we mentioned here, but just which is just a particular way to take this weighted average across the different settings. So this data Shapley score has a lot of nice mathematical properties. And I want to just give you a quick illustration of what this actually looks like in practice. Right, so going back to this dermatology example, sort of our running thread, right? So this is my training data. The training data could be quite noisy because a lot of this is sort of scraped from different sources. And when I take my models trained on this data set and deploy that on real clinical examples, right, the performance of the model can drop, as we saw. Okay, so what the data Shapley score does is that it actually quantifies for each and every of the training image, right, how much did that particular training image contribute to the model's performance in deployment. So the Shapley score could be negative or could be positive, right? So negative would suggest that this data point is somehow detrimental to the model's performance. Maybe it's introducing noise or it's introducing bias. And the data points have positive scores if that point is somehow more informative or has higher signal to noise ratio. So it actually benefits the model's performance on the deployment examples. Right, so here just showing you some examples of data points that have high Shapley scores. So this is actually quite useful for understanding the different potential biases and behavior of the model. And also enables us to sort of quickly improve the model, because one very simple thing that you can do is to take exactly the same model architecture you had before, right? Maybe your favorite convolutional neural network architecture. And instead of training it on my original training data sets, right, I'm going to train it on the original training data set, but now weighted with a weighted score, right? So each training point, each training image now would have a score that corresponds to its Shapley score, right? So this is sort of a very simple idea that encourages the model to pay more attention to data points that we believe are more beneficial or more informative or have higher signal to noise ratios, right? So the benefit of doing this is that you don't have to, you can do this on the existing data that you already have, right? And you can do this on the existing architecture you have. The only difference now is that we're doing this sort of assigning a different weight to the different data points. And this can have quite significant improvements in practice, right? In this particular case, you can actually improve the model's performance by over 10%, right? Just by training it on this weighted data set. So hopefully that gives people an intuition of how, why it's useful to compute the Shapley scores and how we can try to use it in practice. This is, I should say, this is still very much an open area of research, right? And I should also be clear that all of the things I mentioned here are still quite early stages. There's a lot of exciting things that people in this community, in the audience, can do and contribute to. Right, for example, for the data Shapley scores, right, there's a lot of computational challenges. Like computing Shapley score exactly is very expensive. Right, it actually requires an exponential number of computational steps. There's some other statistical challenges, like the Shapley score doesn't naturally account for randomness and noise in the data very well. We made some progress on the technical side towards partially addressing some of these limitations. Right, so we came up with some various adaptive sampling algorithms And in some cases, we're able to come up with sort of analytic approximations to Shapley scores, right, which are very fast to compute because we have analytic forms. We've also proposed these ideas for statistical Shapley values, which are sort of more natural, probabilistic objects that accounts for the randomness in the data. But I think there's still a lot of room for improvements. Great. So the third step I want to mention is to thinking about better ways to evaluate the model's performance with sort of this human in the loop idea. Right. So why do we want to do that? I guess the high level thing is that if you look at most of machine learning, right, most of the time machine learning is often optimizing for the wrong objective. So why do I say that? Right. So if you think of most of the time how ML algorithms are developed, often there's someone who curates and collects the data, right, annotates the data, and that data set is passed off to the machine learning developers, right? And the developers would sort of train and do gradient descent on their model, which is basically optimizing for the model's performance on this some held out part of their benchmark data set. Right? So that is actually not what we really care about, right? We don't really care about optimizing the model's performance for this benchmark data sets. In practice, what we really care about is how well does the model work for my real world usage that I'm interested in. Right? And that's is very hard to do, right? Because ideally, I would like to be able to, during the model development and training stage, I'll be able to collect real world data very quickly, but that has just a lot of overheads, right? So if I want to collect real-time data to evaluate my model, right? For each of the specific domains, I often typically have to create like a domain-specific workflow, right? And it requires a lot of this engineering overhead, right? So in addition to training the model, right? So we'll have to figure out some way to containerize the models that can be deployed, right? In different browsers, in different compute environments. I need to be able to have some data sets or database to store all the different examples and queries. And we have to spend some efforts to build different interactive user interfaces, right? Which is often a research project by itself. And they all require different languages. So it's too much work to make this scalable. So this motivated us to develop this framework led by my student Abu Bakr, which is what we call Gradio. And the motivation of Gradio is that we want to basically do all of these steps, right? Make it extremely simple, right? So it's all native to Python, so it's one language. And the goal of Gradio is to be able to, for researchers and developers to collect real-time feedback on their model within 60 seconds, right? Just in 2 or 3 lines of Python code. So you can go play with it on gradio.app, but I'll just give you a quick illustration of how this works, right? So it's all a Python package, right? So you can just import Gradio. And let's say if you have a trained model that you're interested in, right? Where you're developing a model, in this case, this is my skin classification model, right? I just tell Gradio to generate an interface around this model. And I tell Gradio that the input interface should be an image and the output should be some labels. And then I just simply write, launch Gradio. And what it does is that it creates an URL, and I can just send this URL to any of my collaborators or to any physicians or beta users, right? They can just open up this URL on their browser, and then they will immediately be able to interact with my machine learning model without having to download or set up any environment or anything else, right? So in this case, if they open up this URL, they'll see this interface on their browser, and they can just click or drag and drop in images, and they run the model, right? They can also modify the image by changing its lighting in real time and see how does the model's performance change in real time, right? In this particular case, the model's performance actually changed quite a bit just because of the lighting of the image, which is a potential cause of concern. Then in that case, then the user can just flag it and tell us this could be a problem, right? So all of this can be done extremely quickly, right? Just in these 3 lines of Python, which makes it very easy to collect and to evaluate models, not at the very end after the models being ready for deployment, but throughout the model development stage, right? And this can be very useful for understanding different weaknesses of the model or to retrain the model with these interactive user collected data. So Gradio supports a lot of different interfaces. It can work with image data, text data, video, tabular data, right? It's it's all open source and it's already used by over 10,000 machine learning teams and developers, including ones from industry as well as from other universities. And actually, we're using this also to run some of the first real-time AI trials here at Stanford Hospital, testing some of our dermatology algorithms. Okay, so hopefully that gives people a flavor of these three different steps of the data-centric perspective on AI. Now I want to just conclude by going back to our motivating mystery, this motivating example of what actually happened with this particular dermatology AI algorithm. Right, so if you recall, the reported performance was over 0.9. When we tested on our Stanford images, it dropped to 0.6. So now using the various tools that I mentioned here, right? So we want to understand what actually happened to the model's behavior. So it turned out that one big factor that led to the drop in the model's performance are these label mistakes, right? So the data that was used to train and to evaluate these original Derm AI algorithms, the labels for those data came from dermatologists visually inspecting the images, right? Because that's easy to collect. And it turned out that can generate a lot of mistakes. Right? In contrast, the data that we have here in our data sets came from biopsy samples, which is the ground truth. Right? And we quantify that a substantial number of mistakes are due to the fact that the algorithms are trained on these visual annotations, which are not super reliable when compared with the biopsy validated, pathologically validated ground truth annotations of disease. So that's one big source of mistakes. So the second source factor that contributed to the model's drop-off is data shift. Right? So it turned out that these algorithms were mostly trained on common diseases, because again, that's easy to collect in the public data sets. In our data set, we have both common diseases and also less common diseases, right? And so it's more representative. And that's also a big factor in why the model's performance dropped off. A third factor, which is also very important, is the models, these dermatology AI models, they performed substantially worse on darker skin images, right? So especially if you look at the sensitivity of these models, so obviously how good is the model in detecting diseases, right? So their sensitivity is just especially poor on darker skin images, right? And part of, a big reason for that is that there's very few dark skin samples in the publicly available dermatology data sets, right, that were used to train these models. Right, so this is how we can partition and understand really why did the model really fail in this particular application. Great, so hopefully that gives people a framework of how we think about this data-centric framework for thinking about explainable and trustworthy AI. So all of the code and papers and data sets we have are publicly available. You can find them on my website. I just want to thank again the excellent students who led all of these efforts. So I'll stop here and happy to take any questions.
Thank you, James. This was excellent. Do we have any questions for James? How would you go about modifying the FDA approval process for these types of tools? For example, should we have more multifaceted or nuanced approvals, or will that too be confusing? Should we invest in gold standard benchmark data sets? Who should own or maintain those benchmarks?
Yes, so yeah, that's a great question. Thank you. So first, I should say that the FDA is also very cognizant of these potential limitations in the current process, and so we have a good dialogue with many folks at FDA, and they're very much looking for ways to improve their evaluation process and monitoring process for medical AI algorithms. Right. So there's a couple of approaches here. Right. So one is that for many of the other treatments like drugs, right, FDA often try to rely also on post-market surveillance and monitoring, right, to see if there are side effects or adverse outcomes, right? So I think something like that, analogous to the AI algorithms, could be quite useful, right? So that would be after you have the AI algorithm that's already deployed, then we want to have some mechanisms to continuously monitor the performance of the algorithm, especially on new data sets, or especially if their data distribution shifts. The second suggestion is that just in terms of the evaluation process itself, I think that could also be much more transparent, right? So right now, there's not the companies who come up to propose that develop these medical AI tools, a lot of them do not report very much information about the performance of their model on different demographic subgroups, on different types of patients, right? For example, or the performance across different hospitals, right? So I think we can have a much more standardized reporting framework even, right? So it just says you have to report, to encourage companies to report more granular data stratified across different settings, right? I think those will be relatively, would already go some ways towards improving the evaluation process.
Thank you. I think we have another question. What can be the value or usage of knowing data shapely in the real applications? Could you please give a few examples?
Yes, thanks for the question. Yeah, so I think there's several applications of data shapely evaluation in real applications, right? So first, like in the dermatology application I mentioned here, right, it gives us a good sense of what are the types of data points that are contributing bias or noise to my model's performance, and also gives us very quantitative sense of what are the kinds of data points that ends up being very informative, right? So one thing we've done is actually use the data shapely scores to do active learning, right? To do additional data collection. We've shown that that's actually really a good, useful way to efficiently collect data and also actually performs a bit better than some of the other state-of-the-art active learning algorithms. It's also quite useful just for, for identifying what data points could be mislabeled or have misannotations. We, in some of these other applications looking at chest X-ray, we actually looked at data points that have negative or very low data Shapley scores. And we have gone back and had more careful clinicians and physicians to re-annotate those data points that have low scores, right? And in many cases, a substantial fraction of those low score data points that were just misannotated in the original database or in the original EHR. Right, so it's also a good way to identifying these potential outliers or just mistakes in the data set.
Well, thank you. So if there are no further questions, this completes our afternoon program, although let me remind you that there is still a demo schedule by Virtualytics. I put the link and the passcode in the chat again. So let me finally thank first to the audience who persisted through this long and very information-filled day. All of the speakers who contributed wonderful talks today. My fellow organizers, Yisung, Anima, Kathy, and Adam. Our sponsors, Virtualytics and Amazon Web Services and PIMCO. And finally, I'll note that the technical support for this webinar was provided by the Caltech's Academic Media Technologies and Leslie Maxfield in particular. So this completes our workshop, aside from the demo, and I hope you found it useful and interesting, and you know how to reach all of the speakers or poster presenters. So take care, everybody.